All right, so let's talk about that next graph. So this is going to be one of the most, there's going to be three main graphs that we use to describe motion. One is position time graph, one is a velocity time graph, one is an acceleration time graph. Okay? Time on any of these graphs, you do not have to think, you do not have to guess. Time always goes on the x-axis. Okay? Time is never going to go on the y-axis. Time always goes on the x-axis. Don't have to think about that. Because position is dependent. Position is a function of time. Time is not a function of position, which would get really weird. So, yeah, it would be weird. So you're going to have this nice quadratic function. Okay. So the first thing that you need to realize that this is not linear, because that's one of the questions kids always ask. Hey, when do we draw a line of best fit? This is so much of a curved line, it would do you no good to even try and draw a line of best fit because it's such a quadratic function. Do you need to connect the dots on your graph? Absolutely. Does it make any sense to draw a line of best fit? No. So, when you get to question number 14, describe the relationship between time and position and write a general equation for the curve. So there's a whole bunch of different ways you can answer that question. You can say, if you're wordy, you can say, oh, position changes as a quadratic function of time. You could say position changes with time squared, okay? You could say that it's just a quadratic function, okay? Pick one, I don't care. But what you cannot say is that it's just a direct relationship. Because if you just say it's a direct relationship, that's too nebulous. I don't know if you think it's a linear function. I don't know if you think it's a quadratic function. But you just can't say, oh, it's a direct relationship. Now, then it says write a general equation for the curve. Again, there's options. So if you come over here on the front, you go, oh, this looks like graph C, y equals kx squared. So one option, and this is degrees of nerddom on what you want to do. One option is that you go y equals kx squared. That will suffice, okay? You can just put that down. It's general form. If you want to do this in terms of what you actually graphed, oh, okay, right, my y-axis is my position. We'll call that x because it's like a distance. And then you have k, and then you have time on the y-axis. So that's another option. You can put y equals kt squared. Now, if you actually plug this into your calculator and you do a regression, you can actually find the value of k, and you don't have to. I'm just saying if you did this. And later on, you'll see where this number comes from. And that's 4.9 t squared, okay? Now, if you really want to get fancy, you can put the units on the 4.9. Now let's just think this through. This is where you do dimensional analysis. Your x value is going to be measured in what units? Meters, because it's how far you've traveled, right? Time is going to be in seconds, which is going to be second squared. So what units does k have to have so that when I multiply it by second squared, I end up with meters?
Meters over second squared.
Meters over second squared. Because then the second squared cancels out and I get meters. So the units on that is 4.9 meters per second squared. What's measured in meters per second squared? Acceleration. So the k value is the acceleration of the object, okay? Or you can just put y equals kx squared. It just depends upon how far down the physics rabbit hole you want to go, okay? Now, here's the next question. And this is a huge if. So when you get to question 15, or I type this up in big bold letters, I said if, okay, and this is a huge if the graph had been linear. It's not. That's why I said if the graph had been linear. What physical quantity would be represented? So if it had been a linear function, where you have position and you have time, and it was something like this, okay? So let's say there's 4 seconds, and there's 80 meters, and we start at 0, 0. This isn't the graph, but just stay with me through the hypothetical, okay? Stay with me through the hypothetical. If it had been a linear function. We start at 0, 0, and the other point is 80 meters in 4 seconds. Could you find the slope of that line?
Yeah.
And what would the slope of the line be? 20?
Meters per second.
20. 20 is the math answer, okay? 20 is the math answer. We're not in math class. Actually, we're kind of in a math class. We call it physics. I get cool toys. No, it's true. Jesus, math is really boring. Oh, horrible. So, I get to have squirrels and helicopters. So, if we're in physics class, which we are, then we can say the slope is 20 meters per second. So what physical quantity is measured in meters per second?
Velocity.
Velocity. So if, and this is why I said this is a huge caveat of if it had been a linear function, the slope would represent what?
Velocity.
Velocity. Okay? Because the units are meters per second. Okay? Makes sense. So there's your answer to number 15, right? If it had been linear, and it's not, you would say, oh, the slope represents velocity. Now, let's talk about number 16. So I take the squirrel falls out of the tree. As soon as the squirrel falls out of the tree, what does the squirrel begin to do? Speed up or slow down?
Speed up.
Speed up. Does the squirrel accelerate?
Yes.
Yes. There has to be a force acting on the squirrel to cause the acceleration, because Mother Nature's the lazy thing you're not. And again, get out of your minds the idea that acceleration always means that you speed up. Acceleration just means that you're changing a velocity vector. That's all. Bigger, smaller, changing the direction. Your steering wheel, your brake, and your gas pedal are all accelerators from the physics perspective when you drive your car. So I'm going to drop this, okay? So it's going to drop, it's going to fall. Cool, right. It's going to accelerate. Is it going to go faster? When I drop it, do not make this difficult. Yes. Can't go any slower than 0. Even freshmen can't go slower than 0. I've seen them try. If you're at 0, that's as slow as you can get. I'm going to drop it. It's going to begin to speed up. Now, here's where this becomes a logic problem. So, if the slope of a position time graph represents velocity, which it does, and the squirrel falls faster and faster and faster, so stay with me through this thought process. Slope represents velocity. Velocity is getting bigger. So if the slope represents velocity and the velocity is getting bigger, what has to happen to the slope of the line?
As it changes.
Oh, you said the C word. No, bad. Stop.
As it increases.
Change. It's different. Is it going to get steeper or more shallow?
Steeper.
Steeper. Okay, we're going to go to the senior way, not more shallow like the freshman curve. Okay, this is going to get steeper, right? So, if I come in here, and for those of you that are math nerds, if you remember tangent lines, okay? Oh God, chill out. Okay? So, if you come in here and you draw tangent lines, which represents what we call instantaneous velocity, tangent lines are only drawn on curves. So, if you're a real math nerd and you've studied calculus, you take the derivative of the function, that gives you the slope of the tangent line at that point, which in this case would give you the instantaneous velocity. That's what physics and math cross lines. Here's, we're not, just don't worry about that right now. So here's the thought process. Oh, I dropped the squirrel. The squirrel falls faster. The velocity gets bigger. Therefore, the slope of the line has to get steeper. Okay? And the only way that, and we represent that with a line that is becoming steeper because the slope represents the velocity. So when you answer number 16, I said, using your answer from number 15, explain the shape of the graph. So this is the logic that you want to explain. Oh, right. We just said slope represents velocity. Velocity is getting bigger, therefore the slope has to get
Bigger.
there you go. So explain number 16 in a manner that suits you and me. More importantly, it suits me. So help me, what are the words you are not going to use?
Change or
Change
different.
or different.
Change or different. Oh, horrible. Yeah, let me just make me laugh. Okay.
You saying I look funny?
Huh?
You saying I look funny?
No, I'm just letting you just make me laugh. Your chest.
I would say he looks funny. Whoa, whoa, whoa.
Well, yeah, you're a visitor in this class.
Oh, my bad, my bad.
Okay,
I'm not, I can say it.
that's valid. How many hours on the video game last night? 0.
Liar.
Over?
I had Bible study, so.
Ah.
Oh, that's fair. Proud of you, guys. Thank you.
When I called you, you were sitting at your desk on your desk.
Oh.
You can believe her, you can believe me, but it's up to you. Well, I had Bible study, so I didn't have time.
But yeah, if you lie about being on Bible study versus playing a video, you lie about that, oh, that's like a double whammy, man.
That's a big loss.
Yeah.
That
God
doesn't mean you
strike
can
like
lie. You're
lightning is
on the
gonna go
floor.
come from that ceiling and hit you.
If I was lying.
If. Okay,
So far.
all right, physics meets theology. Okay, on number 17, I'm just gonna briefly talk you through what you need to do on number 17.
Great.
You have 4 sets of data, A, B, C, and D. If you want to graph them, you can. Uh,
My bad.
that was emphatic. Okay? Yeah, I said if. There was a huge if, wasn't
I
there?
heard that.
Okay? If you want to graph them, you can. But basically, what's going to happen, as I say, in which graph is y directly proportional to x? If you can just look at the data and figure that out, great. If you're a visual person and you want to graph it, graph them. Okay? So your answers on 1, 2, 3, 4, 5, and 6 are either going to be A, B, C, or D. And yes, obviously, those 6 answers, you can use one answer more than once. Okay? Now, let's talk about 18, 19, and 20. This is one of the most important skills that you have to have because you are going to use it again and again and again. And that's the ability to look at an equation and figure out what's going to happen if you manipulate one of the variables in the equation. So we're going to start with something simple. Force equals mass times acceleration. Newton's second law of motion. So here's what I'm saying on question 18. So if the acceleration is doubled, what will happen to the force if mass is constant? I'm going to show you 2 ways that you can do this. One is what we call smash mouth physics, where you put in numbers. The other one is a more elegant mathematical approach. How you do this, I care not, okay, but it's one of the most vital skills that you have to have. So let's say you go, Bergkamp, I'm a numbers kind of person. Great. We're going to put in numbers. What's an easy number we can put in for force that's not 0?
10.
1. That's as easy as it gets, 1 Newton. What's an easy value for mass? 1 kilogram. So therefore, the acceleration has to be
2. Whoa, whoa, whoa,
One.
whoa. My fault, King. You said 2.
1 meter per second squared. Because check my math, 1 times 1 gets me 1.
Oh, that makes sense.
Okay? True? So this is actually how 1 Newton of force is defined. 1 Newton of force is defined as the force that it takes to take a 1 kilogram mass and make it accelerate at 1 meter per second squared. That's how 1 Newton is defined, okay? You could have picked 10, 5, and 2, okay? Doesn't make any difference. This is just an easy set of numbers to work off of. Now, I'm going to double the acceleration, but the mass is going to stay the same. So I still have 1 kilogram of mass, but now my acceleration is going to change into 2. There you go. 2 meters per second squared. So therefore, the force now becomes 2 newtons. So what happened to the amount of force that you apply? It doubles. That's why I said you want to be specific in how you answer that question. Just don't say, oh, it increases, or worse yet, it's different, or it changed. If you know specifically how the values are changing, that's how you specifically want to answer that. Now, that's what we call smash mouth physics. Here's the more elegant mathematical approach. And some people hate this method. I'm just going to show you both methods. You have F equals ma. What are you going to do to the acceleration? Double. So instead of a, I'm going to have
2a.
2a. Therefore, to make it balance out, I have to have
2a.
2f. Okay? Pick one. Okay? If you like numbers, do numbers. If you like variables, do variables. Which one you pick, I care not. Okay? Think through it. Now, when you get to that second one, you have distance equals 1/2 at squared. Okay? This is a famous kinematic equation that relates how far an object travels based upon distance. So, again, there's two things you can do. You can do smash mouth. We'll let the acceleration be 1 meter per second squared. We'll let the time be 1 second. You do all that, you get a 1/2 meter. Now we're going to double the time, but we're going to keep the same acceleration. And that's squared. So now we're going to have 1/2 times 1 meter per second squared, but now we're going to have 2 seconds. But the seconds is going to get squared, so that becomes 4, and that becomes 2 meters. So if I take 2 and divide it by 0.5, I get 4. So it's gone up by a factor of 4. So anytime you see something that's squared and you double it, it has a 4-time increase in what you're talking about. Now, again, if you like this, if you like the elegant approach to it, it's the same idea. You start off, you go 1/2 at squared, that's my initial condition. Then I'm going to have 1/2 a, but I'm going to have time is going to get 2t, but that's going to get squared. So that becomes 1/2 a 4t squared. So therefore, to balance out, the distance has to go up by a factor of 4. Okay? Pick one. I don't care. Pick the method that makes the most sense to you. So, this is all going to be due on Monday. We've basically got everything done. The only thing really you have left to do is 17, 19, and 20. So, there you go. I'm done. I know many South people, you guys probably ought to get out of here since I've already stolen you. Maybe against regulations. So, stop you on the camera. Have a great weekend. Yes?